All right, good morning. So here we are yet again for another lovely session of MENG 3310 Fluid Mechanics at the University of Texas at Tyler Houston Engineering Center. This will be the 10th lecture in the series, and today we are continuing or actually finishing up our work on Bernoulli. Bernoulli's principle and its various applications. So I want to, first of all, I want to sort of reinterpret Bernoulli. I've been asked about this before, but I want to sort of elaborate and clarify Bernoulli. We have looked at Bernoulli in terms of energy before, but there is another way you can interpret Bernoulli, and this is a physical interpretation. Bernoulli equation, a physical interpretation. A physical interpretation. So, let us write out the formula for Bernoulli here. Well, if we remember, it's P over gamma plus V squared over 2G plus Z equals constant along a streamline. Which is constant along a streamline. Now, let me label these and we can sort of get a feel or a new interpretation or a new realization for what this is, if I can pick my nouns correctly. So, there is a term. Anyone know what we sometimes refer to P over gamma as? Pressure head, yes, pressure head. Pressure head. We refer to V squared over 2G sometimes as velocity head. And we refer to Z as elevation head. And let us examine the units of each of these. Let's look at this from a unit perspective. So here, let's see, something like, they all have units of something like energy per volume, energy per volume over weight over volume. Over weight over volume. Something like this. Or simply energy over weight. Or if I look back to my fundamental quantities, if I look at my fundamental dimensions, I should say, we'll have fun with this when we get to dimensional analysis later in the semester. We'll have all sorts of fun. Pi terms. L times F over F, or simply L, units of length. So all of these reduce to length as we have this written here. Now the question might be, why would I seek to interpret this in terms of height? What is the advantage of this? Well, the advantage of interpreting all of these in terms of height is it's a very sort of practical and physical interpretation. In other words, if I have a building, for example, if I have a multi-story building, if I want to know how high that this that a pipe can raise water in a fluid or in a building or something like that, or how high the pressure, the ability of the pressure of in a certain tank or pipe, etc., to lift water of certain height. Well, this is very natural. If I measure pressure in terms of height, well, suddenly it's very clear. If I say that I have a pressure head of 10 feet, well, how high can it raise a column of water? 10 feet. Very simple. Same thing with the velocity head and elevation head. It is reinterpreting all of these quantities in terms of height. Now, again, I'll go into this a little more detail here. Elevation head. So let me define each of these or discuss them a little bit. Elevation head. pressure head and velocity head. Okay, so as we've seen before, elevation head is related to the gravitational potential energy of a particle. Let's see. This is related to potential energy of a particle. The pressure head is related to the internal energy. The pressure energy. The internal energy, I should say. So if I look at this fundamentally of a particle, and if I look at it more fundamentally, really where this energy is stored is via molecular repulsion. And it represents the height. The height of water, of a column of water. Oh, if I can. The height a certain pressure is capable of raising a column of water. It is capable of raising a column of water. And I want to go into that molecular interpretation of pressure in a bit. Column of water, or actually I should just say fluid, probably not water. This applies to any fluid. And finally, velocity head, it relates to the kinetic energy of a particle. So this is the elevation head is just the elevation of a particle. The pressure head is the ability of that fluid's internal energy to raise a column of water a certain height. And the velocity head is the distance an object would have to drop or have to free fall in order to have that same velocity. That same velocity. So all of these terms can be all of the terms of the Bernoulli equation can be interpreted in terms of height. The elevation head is just simply the height of the fluid at a certain point. The pressure head is the ability of that fluid's internal energy to raise a column of water, or I keep saying water, any fluid a certain height. And velocity head is the equivalent free fall distance. So all of these can be interpreted as height. Now, if I go back to molecular repulsion, what do I mean by this? Pressure as molecular repulsion. Let me write this in blue here. Pressure as molecular repulsion. How does a fluid under pressure actually physically store energy? Well, if we remember our chemistry, if we remember our physics, there's going to be protons, neutrons, electrons, etc. But in the nucleus, there's going to be protons, neutrons, etc. So you have the nucleus here, and then around it you have the electron cloud. And you have the same thing over here, protons and neutrons in the center. This is high school chemistry, not that difficult. And then you have more electron cloud, another electron cloud. Now, as we know, electrons are negatively charged. Electrons are negatively charged, and as such, atoms don't like to be too close to each other. Maybe this is the distance they would like to hang out by default, or if I just draw the atoms as single points here, consider that. Maybe this is the distance that they will like to hang out at if given the option. Maybe they like to hang out this close to each other based off of, that is where the forces of attraction and the forces of repulsion, there are interatomic forces that will hold molecules together, but there is always the repulsive forces. And so maybe they like to hang out together just this distance. So if I try to force them together, that is going to generate a stronger repulsive force, and if I release them, they will then fly apart. So if I apply a force to these two atoms, if I apply a force, now this is not actually applied as point forces, but you can get the idea. If I have two atoms or two molecules, and I apply a force to them and force them to just directly touch or abut with each other, they will now have a repulsive force generated within them. So they'll want to continually fly apart, even though, and I'm going to have to continually apply that force to prevent that. And so they have a force within them that wants to resist that repulsion, resist that compressive force, and this is a internal repulsive force, and this is ultimately generates pressure. Now, although if I actually wanted to talk about, so that's how it would work if the molecules were stationary, but in reality, we know pressure isn't really like that. It's actually generated from molecules colliding into each other. So it's more of a dynamic thing, where you have a big cloud of molecules or a big pile of molecules all constantly jiggling up and flying and bumping and slamming into each other, and that's what's ultimately generating the pressure force. I am illustrating this as a static thing, but in reality, this is a very dynamic condition. Okay. Next, I want to look at one final interpretation of the Bernoulli equation, and this is basically a pressure interpretation. So we have seen that there are many different ways to interpret Bernoulli, and I can also look at static, stagnation, dynamic, and total pressure. Dynamic and total pressure. So again, we have Bernoulli. I can write it slightly different way with rows. P, if I write in terms of density, I should say, plus 1/2 rho v squared plus rho gz equals constant along a streamline. This will be constant along a streamline. And there are different ways to interpret this. So I have static pressure. So or another interpretation I can use to sort of break this down. Static pressure, this is going to be our P, or our P over gamma. Our hydrostatic pressure. So static pressure is just the pressure that is present in a fluid. Then I have hydrostatic pressure. This is the pressure that comes from the height of a fluid. Hydrostatic pressure, this is rho gz. And I also have dynamic pressure, which is what we saw previously with the common loon in the problem with the aquatic bird in the last lecture. And this is, so dynamic pressure is 1/2 rho v squared or v squared over 2g. V squared over 2g. So again, we can see here that there are many different ways to interpret Bernoulli. We can solve it for different kind of applications, and we can interpret it in different manners. In a sense, we have 3 different ways of looking at Bernoulli that we've explored, and these are, as we've seen, the energy interpretation, the I should say the height, or the height interpretation. interpretation or the pressure interpretation. These are three different ways of looking at the same equation. Interpretation, if I can spell interpretation correctly. And so let me draw out what I mean by the, let me draw out this sort of pressure interpretation again. Imagine I have a pipe here, and there is a fluid moving within it. So if I have a pipe, and let's say that there is a two tubes coming into this pipe. One is going to be connected to the center of the pipe, and the other is going to be just a vertical pipe. So, say I have this, one pipe like this, and the heights, don't worry too much about how tall you draw them, it's kind of all relative depending. And so you're going to have a, let's say this is full of a fluid, and I'll just make it, you know what, I could draw blue, but that would make it clear it's water. But, you know what, as we've seen, this could be any fluid, so I'm going to make it funky and make it orange. Nice C.T. Tyler colors. Okay, then the fluid would end up being raised a certain height in this one, and perhaps a different height in this one. So if you're drawing this, maybe purposely draw one. You can put this one higher or this one higher, but just draw them differently so you're clear that they have different heights. So there's going to be a certain velocity, and here's the center line of the pipe here. And something interesting happens here. So what conditions are needed for this to occur? Well, the reason I have these two different tubes is that they are going to react with the fluid differently. This one is not, this simple vertical tube is not exposed to the velocity of the fluid. It is not, it is merely exposed to the pressure, the hydrostatic pressure of the fluid. And this height, I should say, this height here is going to be, oh, what have I done? I've ruined everything forever. This height here from the center line, sorry, is going to be our H equals P over gamma. And this height here is going to be related to velocity. This H is going to be v squared over 2g. So here, the velocity is directly, basically the fluid is trying to force itself into this tube, but there is an interesting point here called the stagnation point. Right here is called the stagnation point. At this location here, velocity is 0. This is the stagnation point. So a fluid here's where the fluid is stationary. Basically, it comes in, the moving fluid comes in contact with a wall of fluid in this vertical column. So essentially we have pressures, at each of these points there is a balance of forces. Here, this column of fluid in is generating a hydrostatic pressure necessary to counteract the pressure internal to the raw pressure in the fluid. Here, this column of water or this column of fluid is generating a hydrostatic pressure capable of resisting the velocity pressure of the fluid. And so here, these are basically tools we can use to directly physically measure each of these terms. All right, so questions on that? Fairly straightforward, I hope. Then I have one more example problem I would like to work through, if you will allow me. So I have my one final Bernoulli example problem. And if you'll hear me, we'll try to work through this quickly. Example, and this is going to be a nozzle. Nozzle, not mazel. Yes, mazel tov. Nozzle tov. The nozzle. We are deploying the nozzle. Okay, anyway. So, let me draw a very poorly drawn nozzle. It's crudely drawn at best. Prophecy is vague and crudely drawn at best. Futurama references. Okay, so all of this is going to be given. Everything I draw here. I'm going to have a nozzle that comes up and undergoes a change in elevation, and I'm going to label a few points. So let's say there is fluid. Let's just, for simplicity, I'll say this is water. Yeah, this is definitely water. I will have a flow of water coming through here, and it's going to fly upwards out of the nozzle to a certain height. So I'm going to label a few points. First, I have my datum line. I'm going to have my datum line, or my reference elevation. Then from the datum line to the just to the edge of the nozzle, the end of the actual pipe itself, is 1.1 meters. And this is going to be height h. I'm not initially giving this to you. And here, then let's say that at this datum line, the diameter, actually first let me label some point, give you some point labels. This is going to be point A at our datum elevation. I'm going to have point N for nozzle, and then point T for the letter T. That was a joke. Okay. Very poor joke. Anyway, I shouldn't quit my day job. I probably should. I'm terrible at this. Anyway. All right, you pretend to learn, I pretend to teach, you know the drill. Okay, so at point A, the diameter will be 0.2 meters. The diameter will be 0.2 meters, and the pressure at A is going to be 55 kilopascals, which will be a gauge pressure. Okay, so here, and I will also tell you here, I believe, that at point N, the diameter at N is going to be 0.1 meters. Okay, and I am going to give you the task. So all of this is given, and then we are tasked with find H. In other words, given these conditions of this nozzle, I want to calculate how high it will be able to raise a quantity of water, or a stream of water. All right, so you got that, and any questions on the setup on this? I'm going to try to work through this fairly quickly, but we may go a bit beyond time if you will allow me. Okay, so solution here. Well, this is all going to be based upon our fundamental idea of energy conservation. So energy conservation, we are assuming that no energy is put into the system via a pump or something, and no energy is lost to heat or sound or anything like that. The first one is certainly possible. The second assumption is completely impossible. We're always going to lose some energy to heat and such, but you know what, for our simple case here, we can say it's good enough. And I'm assuming that the change in energy from point A to point T is 0. So from point A to point T, I'm going to assume that the change in energy is 0. Now let me write out the Bernoulli equation. PA over gamma plus VA squared over 2G plus ZA is equal to PT over gamma plus VT squared over 2G plus ZT, Z sub T. Now, I can start plugging in some things I know. It is 55 kilopascals. And actually, you know what? In my given, I'm going to put water. Sorry about that. I just want to make sure everything is nice and labeled. So for my PA, I'm going to use 55 kilopascals divided by 9.8 kilonewtons per cubic meter for our gamma, plus VA squared over 2G, VA squared over 2G, so 2 times 9.81 here, 2 times 9.81, 2 times 9.81, oh wait, sorry, not over 2G, that is 2G, derp, 2 times 9.81. Now, at first you may ask, wait, what about VA? We'll get there. And then plus 0, because at A, that's our elevation is 0. Now, here we go. Here's some other things. At point T, what do you think the pressure will be? 0, yes. 1 would be an interesting one, yeah. But actually, yeah, 1 atmosphere, but we're doing this in gauge pressure. So the pressure at point T, at the peak of the flight, will be 0, because it's open to the atmosphere. And our velocity at point T is also going to be 0, just like projectile motion. And then plus 1.1 meters plus h. So this boils down to 4.51. If you run through the math, this will boil down to 4.51 meters plus VA squared over 19.62 meters per second squared is equal to h, essentially. And h will be in meters. Oh, we have a problem. Oh no. What's our problem? We have one equation but 2 unknowns. Do we just give up and go home? Oh, that's not a good attitude. No, we do not give up and go home. We are engineers, or we want to be engineers, or we want to pretend to be engineers. So we do not give up. We do not go home. We finish the problem. Gotta have that good attitude. Anyway, so we need another piece of information. We need another equation to solve for another unknown. Solve for that other unknown. So one equation, 2 unknowns. Now what? We could, yeah, I'll have to use something like that. So let us look at points V and N, or points A and N. So I'm going to use continuity or use a control volume. Or control volume approach. That's a very bad, poorly written C. I really have troubles writing. I need to go take penmanship classes. Okay. Or control volume approach. Or the control volume approach. Okay, so I'm going to look at points A and N. Point A being the datum, and point N being the peak there. Okay. Now, looking here, I'm going to say, okay, so points, back that up. Points A and N. Points A and N, which is the nozzle, right at the edge of the nozzle. Okay, so I'm going to look at this in terms of continuity, and the basic idea here is that as we look at this control volume, if I look at the nozzle as a box or a control volume, here, something like this, if I look at this control volume here, we'll talk about this more later in the semester. But the basic idea is, as long as I believe in the conservation of mass, all of the mass that is coming in one end has to be going out the other. As long as this is a steady state, there's no bubbles or something like that, it's not like I'm turning the hose on just at that moment. As long as we're in a steady state problem or situation, as much mass is flowing in must be flowing out. So, rho VA, and this is lowercase v for velocity, Generally, if you don't recall, I use V with a bar on it, a capital V with a bar on it for volume in this course. So rho times velocity times the cross-sectional area, this is the mass flow rate, for point A is going to be equal to rho, that looks like a P, rho times velocity times the cross-sectional area for point N. And, well, this is going to be water, so it's not a gas, so we can assume that it's incompressible, so that'll go away. And I can then solve for VA. VA is the Veterans Administration. Oh, wait, that's true, but irrelevant here. Is going to be VN times, I made a government benefits joke. Anyway, AN times AA. Some people may think I need AA, but that's another thing entirely. Is going to be equal to VN times simply the cross-sectional areas, which will be pi over 4 times the diameter squared, or 0.1 meters squared over pi over 4 times 0.2 meters quantity squared, or simply Vn over 4. Vn over 4. And that's my lovely handwriting. So what I have now is VA equals Vn over 4. Great, I got more unknowns. Lovely. So we're not quite there yet, but we're almost there. So we have one more piece of information. Now, I still need one of these two velocities, so I'm not quite where I need to be yet. So let me annotate this a bit. I still need one of these two velocities. Now what? Yes, I can do a Bernoulli from A to N. So I can do PA. Again, I'm going to do a Bernoulli. Can I use Bernoulli? I should start using Bernoulli as a verb. I'm just going to Bernoulli this thing. I'm just going to Bernoulli it. Anyway. And maybe you can just start using Larson as a verb too for just generally screwing something up. Anyway, so PA over gamma. PA over gamma plus VA squared over 2G plus ZA is equal to PN over gamma plus VN squared divided by 2G plus ZN. Oh, is that. Okay, now I can start eliminating some things. First of all, I can say, okay, well, ZA is 0 because it's at the datum, and PN is 0 because this is gauge. We're dealing with gauge pressure. It's open to the atmosphere. And so then plugging and chugging, I can, what I'm going to do is I'm going to substitute in, I'm going to substitute this in for Vn. So I'm going to substitute VA, that expression for Vn in for VA. Now, here, let's see, how might I work with this here? I am going to say that 55 kilopascals over 9.8 kilonewtons per cubic meter plus VA squared over 2G equals 0, 0 is equal to VA for VA. If I solve this for Vn, I get Vn equals 4 VA. So I want VA because that will be useful in my next and final step. I'm almost done. Just bear with me for a moment. Over 2G, I'm not going to solve this all the way through. I'm just going to set it up and show you what result you'll get because I think you can do algebra. And if you do solve through this, assuming I didn't screw this up, you will get VA is equal to 2.43 meters per second. VA is 2.43 meters per second. And now, at long last, I can plug into, let me go back and maybe star this equation here. This equation here. If I go and plug this one in here. So if I then go and plug into the starred equation, take the VA of 2.43 meters per second. If I then go and plug into the VA value equals 2.43 meters per second into the starred equation, I cannot write a star, equation, you will get, well, finally, H in meters is going to be equal to 4.51 meters plus 2.43 meters per second quantity squared over 16.92 meters per second squared, and 19.62, 1692, 1962, same thing. 19.62 meters per second squared, and finally I get an H of 4.82 meters. 4.82 meters. And there you have it. So that's my final example of working through the Bernoulli equation. Thank you for humoring me today. I hope you learned a little. I hope you learned a lot. So as a reminder, we'll have class again on Friday, exam on Monday. If you have any questions, feel free to drop by my office hours. And as always, thank you.